So let's try to solve the two-dimensional steady state heat equation. That equation we also called as Laplace equation. So we have been given the problem that there is a steady heat conduction in a square slab. So it is shown, and the upper and lower sides are maintained at T is equals to 100 degrees centigrade. Therefore, the this temperature on upper boundary is 100 degrees centigrade, and lower boundary as well is 100 degrees centigrade, whereas the left boundary is at T is equals to 50 degree, and the this boundary is also at 50 degrees centigrade. Now we have to solve this problem analytically. So what in general we have seen that while two-dimensional Laplace equations are given, any one of the boundary layer is mentioned as the fixed temperature, and so as to make the problem easy, whereas in this problem we have taken the all the four sides of this square has been mentioned the boundary value temperature. Therefore, the governing equation governing equation for this heat generation will be given by dou by dou t rho Cp T is equals to dou times of K dou T plus Q heat generation. Since we are taking as a steady heat, it will be 0, and no heat generation we are taking, therefore it will also be 0. Therefore, this can be written as del square T by del x square plus del square T by del of y square is equals to 0. So it is a two-dimensional partial differential equation. Now we have to solve this analytically. Now in this problem, what is there that all the four values have been specified along all the four edges of the square. Therefore, this problem will be solved by superposition principle. So before doing that superposition principle, we will do a mathematical just adjustment into this. Now we are taking a variable theta such that theta is equals to T minus 50 degrees centigrade. Therefore, on doing this, we have values on this edge. So this will become 50, this will become 50, this edge will become 0, and this will also become as 0 degrees centigrade. Therefore, if we solve this problem differently for top and bottom edge as theta 1 plus theta 2, then theta will be the summation or superposition of these two boundary condition, and in that we will have to add the 50 plus 50, theta plus 50 will give the final solution in that case. Now first we are taking the top boundary as the initial solution. So let's again redraw. So first we are determining the theta 1. So as we know that theta is equals to theta 1 plus theta 2, and we are taking this theta as 50 degrees centigrade here at top boundary. Therefore, solving the case or first theta 1. Now, this theta 1 is a function of x and y, where x is a function of f of x and y is a function of f of y. Therefore, the equation, if we write del square theta upon del x square plus del square theta upon del y square is equals to 0, where theta is equals to t minus 50. Therefore, putting theta is equals to xy, I will get y times of d square x upon dx square plus d square y upon small d of y square is equals to 0. Putting theta is equals to x into y into the above equation. Now rearranging these, this can be written as minus 1 upon x d square x upon dx square is equals to 1 upon y d square y upon dy square, and this we can assume as lambda square. Therefore, from our basic engineering mathematics we know that this theta 1, the solution can be written as a cos of lambda x plus b sine of lambda x into c into e to the power minus of lambda y plus d into e to the power lambda y, where a, b, c and d are constants. Now we have to determine the values of a, b, c and d, which are constant, by using the boundary condition. Therefore, this is the square and this is the x direction and this is the y direction. Now theta is equals to 0, as we are assuming this theta is also 0. This theta is 0 because we are using the principle of superposition, and for the bottom edge we will solve this as separately. This theta is 0 and this theta is 50 degree. Therefore, applying the boundary condition, first of all we are applying the boundary condition at x is equals to 0, y theta is 0, that is the left edge. When we apply the boundary condition at left edge, so this gives us the solution as a cos lambda x into c e to the power minus lambda y plus d in e to the power lambda y is equals to 0. B sine lambda x will become 0 for x is equals to there 0. Therefore, in this situation, either this term has to be 0 or this term has to be 0. Therefore, this second term, if I denote this as second term, this as first term, this second term can't be 0 because theta will become 0 for all the values of y. Therefore, for this situation, a cos lambda x assuming 0, therefore in this case a will become 0. Therefore, the previous equation theta 1 can be updated as theta 1 we can write as b sine of lambda x into c e to the power minus of lambda y plus d into e to the power lambda y. So this is the updated equation. Now again using boundary condition at bottom edge where x and y is equals to 0, we have value of theta as 0. So we are applying the condition at bottom edge. So what will happen in this case? This theta will become 0 for b sine of lambda x into putting this value of y0 c into e to the power 0 plus d into e to the power 0. We are getting this theta as 0. Therefore, here this b sine lambda x can't be 0, otherwise for all values of x it will become 0. Therefore, writing as c plus d is equals to 0, this implies c is equals to minus of d. So our equation can further be updated as theta 1 is equals to, putting this c is equals to minus 1 into this above equation, we get theta 1 is equals to b sine of lambda x, and replacing c with d and taking out as common, we get d into b sine lambda x is equals to e to the power lambda y minus e to the power minus lambda y. So once again we have this updated equation. Now further we have two more boundary conditions left. So trying to solve those boundary condition. Now we have the equation is 1 is equals to bd sine of lambda x e to the power lambda y minus e to the power minus of lambda y. Now we can write this bd as e. Therefore, this theta 1 can be written as bd as e sine lambda x e to the power lambda y minus e to the power minus of lambda y. Now further using the boundary condition at x is equals to L and y, theta is 0, that is at the rightmost edge of the square plate. So this will become sine of L lambda, and now we can write this e lambda y minus of e to the power minus lambda y in the hyperbolic function. Then it will become sine of hyperbolic of lambda y, and 2 will come here, so this will be written as 2 sine of lambda L sine of, this is now becoming the hyperbolic function, so you need to revisit. So this is hyperbolic of lambda into y, so this will become as 0. Now this, now we cannot make this lambda y 0, therefore sine of hyperbolic lambda L is 0. This implies we can write lambda into L is equals to n pi. This implies lambda we have determined as n pi upon L for all values of n as 1, 2, 3, 4. Now final boundary equation condition at top edge we have to use. So this is at value of x and y is equals to L, theta is equals to 50. Since it is a square plate, we are assuming x and y both equals to L. Therefore, writing this as 50 is equals to, this e will become now en for all values of n from 1, 2, 3, 4 and so on n. So this 50 is equals to en sine of n pi upon L into x into sine hyperbolic of n pi. This is the now final equation. Now we will have to use the Fourier half series in this. Therefore, for this above, let f of n. In this en I have this merge the 2, this 2 I have merged this into en value. Now to simplify this, fn is equals to, I can write as en sine hyperbolic of n of pi. Then f of n can be written as integral of 0 to L 2 by L 50 sine of n pi upon L into x into dx. So simplifying this, we get fn is equals to 100 upon L, sorry, into L upon n pi 1 minus cos of x from 0 to n pi, changing the limit from x to n pi and assuming n pi n upon L as z. So this basic integration can be used. Now if this n is odd number, then this will become 0. Therefore here n will be now only 1, 3, 5. Therefore this fn will become 200 upon n pi. This L and L will cancel out. So we have derived the value of fn from the above boundary condition, where this is important, where n varies from odd number 1, 3, 5 to so on up to infinity. Now we have determined the value of fn as fn is equals to 200 upon n pi. So using this value of fn to convert the equation, now we will determine the en. So en will be given by 200 upon n pi into 1 upon sine hyperbolic of n pi. Now putting this value of en into the equation, which is this one, into this equation, we can get as theta. So theta 1 from this will be given by 200 upon n pi sine of n pi upon L into x, then again sine of hyperbolic n pi upon L into y, and in the denominator it will come as sine of hyperbolic function into n pi. Now this, where summation term will also come, where n equals to 1 to infinity, and this n will vary from 1 to 3, 5 and up to infinitum. So this the value of theta we have determined. So this was for the top edge. Now similarly we can now use the bottom edge. So using this, theta is equals to 50. Now this theta assuming 0, this is 0 and this is now 0, we determine the theta 2. So in the similar procedure, if we solve this theta 1, then we get the theta 1 as the solution, which will be given by summation of n equals to 1 to infinity 200 upon n pi, and this will be given by sine of n pi upon L into x sine of hyperbolic n pi upon L minus y divided by sine of hyperbolic of n pi. Therefore, theta will be used determined by the superposition as theta is equals to theta 1 plus theta 2. So summation of the above two equation in this equation will give the analytical solution of two-dimensional heat equation, that is also we called as the Laplace solution. Now I have determined the value of theta for various values of n in the MATLAB, and what we are getting I will show you in the MATLAB program. So this is the MATLAB program for the above analytical solution. So I'm determining the value of temperature at this x is equals to 0.5 and y is equals to 0.5. So this is a similar equation, 200 upon n pi sine n pi x into sine hyperbolic n pi 1 minus y divided by sine of hyperbolic n into pi plus 200 upon n pi sine n pi by x sine of hyperbolic n pi upon into y divided by sine of hyperbolic n pi. Now we are determining the at the center of the plate, then this x is equals to 0.5 is equals to zero point 0.5, we are getting the value as 75. Again, if I change the value, suppose I want to determine at x is equals to 0.1, then the value comes as 58, as left hand of the plate was at 58 degree. We can visualize the as from here. So this is the left edge which is at 50 degrees centigrade, and top is at 100. So now I have determined the value at x is equals to 0.1, so the value is coming as 58. Now if I do this as x is equals to 0.5 and I do this y is equals to 0.98, that is near to the top edge, I am getting the value as 98.33, that is very close to 100. So it means that the our analytical solution that we have derived is exact and correct. So this we have discussed in detail, and this is the two-dimensional heat equation, also called the Laplace equation, and this is the final solution, and this is the equation. So for theta 1, the equation we have derived, and for the bottom is theta 2, we can be derived very similar, applying the boundary condition in all three edges one by one and deriving the constant, and after then the value of theta 2 can be derived. So this is the two-dimensional solution of heat wave equation.